Hello students, we were discussing about the narrowband interference cancellation mechanisms in the spread spectrum receivers. In that context, in the last module we have already discussed about the time domain adaptive filter architecture, by means of which how we can reject it. We also saw that time domain adaptive filters can efficiently reject the narrowband interference if the adaptive algorithm converges, and hence there is a possibility that if the interference is dynamic in nature, I mean it is a time dependent, interference is time dependent, then time domain adaptive filter may not be able to a good approach, because they cannot trace the time dependent interference. So, is the today's discussion. Let us see actually how we can try to track the dynamic or time dependent interference, and the architecture that can do it, the methodology that can be applied to trace it is a transform domain processing. Transform domain processing is basically it involves a transformer or a transform domain processor. I hope you remember that this processor or this processing block in the receiver is coming in between the matched filter and the dispersing unit. We saw in a diagram in the last module that the incoming signal, after getting multiplied with the local carrier frequency, it is coming down, and then it is passing through the match filter, and the output of the match filter is sampled, and that sampled signal is now entering into the processing block. What processing block? The processing block which is helping us to cancel the narrowband interference, and the output of this processing block will be fed into the dispersing block. So, like inside the processing block, according to the last module, you are either utilizing the time domain adaptive filter or the today's discussion, that is the transform domain processing. So, as the name suggests, this architecture will consist of a transform domain processor, and where actually inside the processor, the input of the processor, you can give the continuous domain signal, and it feeds a real time transform domain processor, and it that transform domain processor may be a real time Fourier transformer, which is implemented as a cheap as a sharp transform processor. And to be practical in sense, the input that is coming, the real sample values that are coming as input to the transform domain processor, that samples are basically coming from the match filter, and this match filter is a cheap matched filter. We understand that in the receiver, direct sequence spread spectrum receiver, the match filter is matched to the cheap waveform, and these inputs, hence they are consisting of the output samples of the cheap matched filter, and as a block of these chips from the matched filter, a certain block, and the block of the chips will be entering into the transformer. Here we consider that the block of the chips is a size of capital N, and the transformer which is denoted in this side, this block, it may be a real time Fourier transformer, or it may be a wavelet transformer. This Fourier transformer may be a discrete time Fourier transformer also, and or the wavelet transformer can come into picture. So, if this is the fundamental block, after the transformer we are having a block called exciser. Output of the exciser will be fed into an inverse transformer, and here actually output of the inverse transformer will be fed to the displacer. Remember, transformer will transform the domain of the incoming signal, change the domain of the incoming signal. Exciser is fundamentally the block who will help us to reject the interference or suppress the interference in the transformed domain, and once actually the interference suppression is done, inverse transformer is in the place to bring the samples back to the original domain. So, how the transformer, what is the target of design for the transformer is, we will see in the next slide. The transformer is selected in such a way that the transform domain forms the desired signal as well as the interfering signal such a way that they are distinguishably they can be distinguished properly. The properties of them we exploit to design this transformer, and how actually the desired signal and the interference will be different in the transform domain is it depends actually how you are doing it, transforming them. And fundamentally when the transformation is there, when the transform processing is done, you will be able to see that if I see the different beans in the transformed domain, you will be able to find that the interference components will be confined into certain beans rather than spreading over all the beans. And if I see the amplitude of the signal component, desired signal component, and the amplitude of the interfering components, you will see the amplitude of the desired signal is uniformly constant over the multiple beans. Okay. Whereas the amplitude of the desired signal you will be finding the approximately constant over the multiple beans, whereas the amplitude of the interfering signal won't be that. And hence what exciser does is once identification is over that in which bean the interferers are present and or the interfering signal is present, then exciser put the coefficients of that bean to be 0. And basically putting those coefficients 0 means it is a complete suppression of that complete suppression of the interference inside that bean. And as we understand that interference is present, the interfering signals are present in only one bean or a small portion of a typical bean. Hence, putting zeros to the small portion of that of the whole bean architecture, partially actually that portion is turned down to be 0 by the exciser. It has negligible effect hence over the desired signal. And now your actually output of the exciser, you are getting transformed bean with the mostly actually the cleared with the cleared desired signal, and hence inverse transformer being this signal cleared signal to the original domain. Instead of setting 0, purely setting 0, exciser can actually put some minimal value also in some cases. But this is the overall philosophy or the way the transform domain processor works, and the exciser helps us to do the suppression in the interference. And remember that in spite of actually deciding that in which beans the things are there, the interference is there, the task is not easy to detect. We follow the methodology like this. Suppose if we are trying to search in which bean the interference is there in the transform domain, we try to actually measure the value of each and every component of the bean, and we measure compare the amplitude of that typical component with respect to a threshold, predefined threshold. So, whenever actually the threshold is crossed, most of the cases maybe actually it is amplitude or maybe the typical amplitude of the interfering signal, because interfering signals come with a higher power usually. And so, we can put the threshold and choose the threshold in such a way that for interfering signal only the threshold will be crossed most of the time, and hence the detection power process is over. After detecting the bean and the components itself, it is easy now for the exciser to suppress them by putting zeros to those components. And we can actually deploy another kind of the filter architecture inside the exciser to perform the suppression of the interference if the interference is static. For this stationary narrowband interference, we prefer to deploy a transform domain adaptive filter as an exciser. So, what this adaptive filter does is this filter adjusts for each and every bean, it adjusts a non-binary weight vectors. So, it puts actually the weight for each and every weight vector for each and every bean output, and it is an adaptive filter. So, the adaptive algorithm tries to minimize the difference of this weighted output of the beans and minimize the difference between the weighted output of the beans and the desired signal. So, suppose your desired signal is a PN sequence and you understand actually what will be the value of the desired signal in the transform domain. Now, you here actually the problem statement is you adjust the weight in such a way that the actual or ideal conditioned value of this desired signal in the transform domain and this weighted value of this transform domain, the error between these two is minimized. And that is the task of the adaptive algorithm itself to go ahead with. And remember, it can be done very fast also easily if the spreading sequence that is used to spread each and every symbol, transmitted symbol is same, number 1 is same, and you are using a short length sequence. So, what's the situation is you are using, suppose if I am measuring capital N number of the chips and capital N number of chips are constituting one symbol, symbolic symbol, and the PNs and the spreading sequence that is used for each and every n chips is exactly same by the transmitter, used by the transmitter is exactly same. In such situation, you need not to actually, you can actually speed up the exciser process by storing the transform domain values of this short sequence inside a memory, but in a read only memory. So, that you can invoke that and whenever the comparison will go on for symbol to symbol basis. And remember, always we are also considering that at the input of the processor there is a input to the processor is always having a block of capital N chips. So, the number of the chips within a block is not changing and spreading sequences for block to block is exactly used to be exactly same. Then by storing the desired signals transform values in the read only memory, we can speed up the process of the exciser. What if there are long spreading sequence is used? If a long spreading sequence is used, then we are helpless, and for the every desired signal, to get the every desired signal transform output, you have to really take the transform, you have to really put the locally generated PN sequence, a locally generated code sequence at the to the input of a transformer, and then he will generate the values of the transformed values in the transform domain for the typical receiver code. The main advantage that we will be getting by this adaptive filter structure putting inside the exciser is that the convergence rate actually it can be actually very nicely or very efficiently suppressing the interference, but with the restriction, with the disadvantage or the criticality that the adaptive algorithm again, like the time domain adaptive filter, again the adaptive algorithm needs to converge, and that cannot be done. That convergence will never happen very rapidly if your interference is a time varying interference. Now, let us assume that transform that operates on a disjoint block of capital N input samples. We define that in terms of capital N orthonormal and in component basis vector. So, this is a transform that operates on capital N. I told that the chips are coming in at the input of the processor at a block of capital N chips, and we consider that there are disjoint such capital N number of the chips constituting one block, and we consider that the transform is happening by capital N input samples, capital N orthonormal and vectors and orthonormal basis vectors. Orthonormal basis vectors, the component of those orthonormal basis vectors are given in this equation 1.1, and which this vector spans over the linear space of dimension capital N, and each of the component of this vector may be actually a complex quantity also. So, if it relies on the orthonormality, then it implies that the theta I Hermitian with multiplied with theta k should always give 1 only if I is equal to k, otherwise it should give 0. We took Hermitian, H stands for the Hermitian operator, which denotes the complex conjugate operation over the vector over the component. We took it to be Hermitian because we understand that these components can may be actually complex. Now, the equation 1.3 suggests what is the incoming signal vector. X is the incoming signal vector given by x 1 to x n, and so each of these vectors can be now each any component of this vector I can express in terms of the basis function like equation 1.4, where this new component that is introduced here is C I, and C I is given by the theta I h into x. Now, if I think that the transformer that where this block capital N block of the input chips are entering, this transformer is a Fourier transformer. It is a Fourier transform. So, we were making a Fourier transform domain processing, and in such cases there is values of this theta i's, the coefficients, the orthonormal basis function coefficients, it will be given by the e to the power j 2 pi I k by capital N. This is a known values to us, but j is equal to plus minus j is equal to square root of minus 1, and this transformer then will be able to extract the values of all the C i's. So, if I have capital N number of the input chips, I will be only interested on the capital N number of the vectors coming out of that structure of the transformer. And now, once you are having the values of the C, we can compute the value of C from the B Hermitian X, where this B Hermitian is nothing but the unitary matrix of all these basis vectors. Now, when exciser is in the path, exciser this then weights each of these component of the transform C by computing the exciser weight like this, where this W d is nothing but a n cross n diagonal matrix, and where the diagonal elements will be put as W 1 to W n. Now, the inverse transformer that was actually last following the exciser, he will then produce the excised block output applied to the inverse transformer, and then whatever the output coming out from the inverse transformer that will go to the displacer is basically given by again B into E. If I substitute the value of the E, then we are ending up with W d into C, and if we change the value of this C again, we can write down B Hermitian into X. Remember here one thing, if my W d, this n cross n diagonal matrix, if it is an identity matrix, then all the entries will be 1. So, if I consider that W d matrix is an identity matrix, then we end up here with B into B Hermitian. Remember, B into B Hermitian will always give you another identity matrix. So, in that typical situation, when W is equal to identity matrix and B Hermitian is obviously will be Hermitian matrix, then you are ending up with the fact that Z will be equal to X. So, output is basically you are getting as the desired signal only. And in order to achieve that, please remember that the transformer and the inverse transformer both will be in tandem. And so, now the question is in general there is diagonal elements of this of the matrix W. This W d, they are either set by the threshold device fed by C, or they are the outputs of the weight control mechanism of the adaptive filter. So, the entries of the W will be either from the threshold device that is fed by C, or otherwise it will come by the weight control mechanism of an adaptive filter. Now, we are talking about a block of the capital N chips. Let us have a situation when this capital N equals to the processing gain of capital G, and then the input comprises of the unmodulated spreading sequence, and the displacer correlates this input block with the appropriate segment of the spreading sequence to form this decision variable. So, what we are doing? We are having the incoming unmodulated signals, and we have a locally generated codes, and we are multiplying it, and we are taking the addition over the processing gain. The filtering and this dispreading both actually. So, first is your filter and then is the dispreading operation. So, this filtering and this dispreading, it can be simultaneously performed also in the transform domain. How? Let us see. Suppose P is that signal, that locally generated code signal that we will be dealing with, and let us assume we are restricting this discussion for a length of capital G number of the chips, where G is also the gain, processing gain of the system. And now this capital P vector, this small p vector denotes the synchronous replica of the spreading sequence, which is generated by the receiver code generator. Now, see, recall that we have seen these two, we have seen already these two equations. The equation number 1 was on the Z. We saw that the expression for the Z is was coming from the B into the exciser output, and it is the weight B into the exciser output, where the exciser is actually basically the n cross n matrix of W and multiplied with the weight vectors this C component. And if I further replace the C by B Hermitian X, and we saw that the expression for the Z is finally governed by the B W D B Hermitian into X. And we have considered the vector P such a way that the P is actually our code sequence. Now, if I substitute this one and this one, where into the expression of the V that we have seen earlier, come here in the equation 1.11. So, this value of P and then value of the Z are now known to us according to the equation this and this. If I put both these values into that V, then V will finally be obtained as P transpose of Z, and Z is again your B W D into C. So, we are finally ending up with a decision that is going on. So, V is what? V was actually the decision variable, the final decision variable about the transmitted message. This vernal value of this message, the decision is now basically dependent on this parameter C, B, W and the designed code P. Now, one important thing, if the spreading sequence you design in such a way that it produces this equation, this matrix P transpose B into W D, produce the matrix P transpose B W D into C. If this is a matrix that we can produce by the choice of a proper spreading sequence, then this product, then the product of this matrix and the transform matrix C will return me back the original V. So, when this kind of situation happens, the spreading sequence is taking care of producing the matrix which is actually required for the final decision, and hence in practice once this kind of the transmission is going on, then the product of this whole with the matrix itself and the transform C gives this V back without how we have got this decision. This decision is now without the inverse transformer and separate dispreader requirement. You can actually delete completely. So, if the decision is out, spreading sequence has taken care of all the part, and hence you need not to put any inverse transformer as well as a separate dispreader to dispread the signal and detect the signal. So, automatically dispreading and filtration operation is going inside the architecture automatically because of the proper choice of the length of the sequence as well as on the quality of the sequence involved in the processing. So, this is all about how the transform domain processing works. So, I repeat that we started with understanding that the time domain adaptive filter is not so good in the case of your in narrowband interference handling when the interference is varying over the time. So, we were trying to see is there any other architecture which can nicely handle this. The answer was yes, and the possible architecture is the transform domain processing. Inside a transform domain processing, basically we see a transform domain processor which takes the inputs from the matched filter, and the matched filter is the sampled matched filter output it is taking at in a block of the n chips. The inputs are coming into the transformer, and these inputs come from the matched filter output, and where matched filter is matched to the chip waveform. And we have also seen that inside the transformer, this transformer can be a real time Fourier transformer, or it can be wavelet transformer also. The transformer is designed in such a way, the transformation algorithm is designed in such a way that in the transform domain easily you can distinguish between a interference and a signal, desired signal. And as actually over the, if I see the output of the transform over the different transform domain beams, you will also see that the interference is residing in a short beam, in a small beam, compared to the uniform amplitude of the desired signal that is spread over all the beams. And so, by detecting, for detection of those when which beam the interference is there, we do a threshold comparison, and output of this threshold comparison will identify the location of those beams where the interference will be maximum, and then the interference will be also out and will be suppressed by the exciser by putting zeros to those beams. Okay. The exciser can be also implemented by an adaptive filter architecture. If you feel that the interference is static in nature, so exciser can also do that. And that time the adaptive algorithm selects the non-binary weights for the output of each and every beam, and your algorithm should be designed in such a way that the weighted output and the desired signals transformed output will perfectly match with each other with minimal error. And if it satisfies, then by some mathematical derivation we have shown that the output can be easily be a function of, easily can be retrieved, and it can be also possible that we need not to utilize any inverse transformer and the dispersing operation finally to get the signal back. Rather, actually for some typical situation, the code design itself can handle the issues. So, at the absence of inverse transformer and as well as your dispersing operation, the dispersed signals, decision on the dispersed signals output can be taken easily. So, exciser has several kind of the roles, not only the suppression. Sometimes with proper design of the code, we can also delete the inverse transformation and dispersing operation also by a proper design of the filter. So, filtration and dispersing jointly is possible to design inside the exciser in transform domain.